Okay, comparator is a type of op-amp circuit that compare two input voltage and produce an output in either of two states indicating the greater than or less than relationship of the input. This is the circuitry for comparator. Okay, they compare input positive to the input negative. Okay, you see which one will be higher. If the input positive higher than a negative input, the output will be go into blood V saturation. Okay, you understand op-amp saturated? The V saturated will be around less than power supply voltage around 1.4 volt. Okay, and if a negative input higher than the positive, then the output will be going down to minus V saturation. That's a very simple, okay? And now, if you're looking on this sideways on the input positive, okay? And the other side negative connect to the ground, that means 0 voltage. So this is a positive higher than ground. So the output will be go into positive saturation. And when the input is negative, they will be less than ground. That means the negative input higher than positive. Output will be go to minus V saturation. You can see that's a very, very simple. However, when you see the symbol for the op-amp, then you need to recognize, is it the inverting amplifier, differential amplifier, non-inverting amplifier follower, okay, or comparator. You can see what the big difference. When you're looking into the circuitry, you know right away, this is comparator. The thing is, in the lecture, we're giving you more detail. However, normally they're not. But the question is, when you're looking into the op-amp circuitry, how do we recognize this is the comparator? Oh no, let me know.
No feedback.
Exactly. You can see the circuitry comparator, they don't have any feedback resistor. Okay. And you can see they say 0 level detection. That means they compare with the one input to the route. Okay. Like we already showed you here. If you get any question, just let me know, okay? Make sure you understand.
See, I have a question, teacher.
Yeah, go ahead.
In this circuit, you don't have any resistor or any passive element?
No, not only, you don't have only feedback resistor. That means the resistor connect from output back into the input.
Okay, thank you.
Only the feedback. they still get some resistors later on, you can see. But when you recognize a comparator, then you have to know what the input at the positive, what the input at the negative. Try to see which input will be higher. If positive higher than negative, output go to positive saturation. And if the negative input higher than positive, they go to negative saturation. That's the only thing you need to know. Make sure you know that. And now, you can see here, this comparator, V in connect to the positive, and the input negative connect to the reference, V reference. If you're looking on the circuitry, V reference at this point, you easy to calculate it. Voltage divider, you take V reference equal V1, that means the voltage here, time R supposed to be R2, divide R1 plus R2. So this is the wrong in here, okay? You change that one. This is the V1 here. And V reference time R2, okay? And divide by to the R1 plus R2. So now they not compare to route like the other one. They compare to the certain voltage. That means we call a V reference. And the first thing you have to do, have to calculate the V reference. Okay, V reference here. Okay, V1 time R2 R1 plus R2. Before you compare that, okay? In showing you, they just show what the V reference and this the V in, and they try to compare. Now, you know the V reference. You already calculate, okay? And this is the V in. So you get a sideway here, okay? So now, at this point, okay, right here, from 0 up to here, then V in less than V reference, right? No matter what V in, equal. However, in the sideway, we can see from here up to here, they less than this reference. So the V out will be go into negative saturation. Okay, now from here to this point, V in higher than reference. Okay, so the output now go into V positive saturation. Okay, then from this point, go to this point here. Basically, they compare to V reference. V in will be less than V reference. So that's why V out now go to the negative saturation, okay, and so on. When you're looking into this display, make sure you understand how come you can get the V out at the negative saturation or the positive saturation. Okay, any question? If it's not, we go here. Okay. Now, on this one, you can easily recognize. Input now will be compared to the inner diode, VG. Okay. If VG, okay, I can give you, you can get a sideways. Okay, and you can get a V in. And VG, I can give you the same thing, VG. So you can see the output will be the same thing what we just learned. So this will be negative saturation. And this will be positive saturation. That's the same, exactly the same. V reference. Okay. So it's basically just a V reference. Either they can use in a diode or they can use in like voltage divider, doesn't matter. Okay. Now let's see what they want here. Example. The input signal as so is applied to comparator circuit. Draw the output showing its proper relationship to the input signal. Assume the maximum output of the op-amp plus V saturate 12 volt and minus V saturate minus 12 volt. Okay, first thing, what I want you to telling me, what the value of V reference. Do that calculation and tell me what the value. What you get?
1.64.
What?
1.64.
Okay, exactly. V reference 1.63 volt. That's okay. Okay. So now in here, I can draw V reference.
Yeah, 1.6.
Yeah, exactly. 1.6 volt. That we reference. So now the input less than 1.6, then the output will be negative. Okay, they will be negative from here. Minus 12. Okay, and at this point, you can go down. It's higher than 1.6. So okay, they will be go to positive saturation. This will be a 12 volt. And in here, they will be less than. Then they go to the negative saturation. Okay. That's a very simple thing. Okay. What else?
I have a question, teacher.
Yeah, just a minute. This is the answer for that. Okay, now question.
Yeah, the question is if the saturation voltage have to be symmetric, 12 minus 12, or I can use 0 in one of this.
You mean for V saturation or what?
Yeah, for saturation, need to be symmetric, 12 minus 12.
Positive, that means 12 volt. And negative will be minus 12 volt.
Right, but can I use 0?
That they given to you.
Okay.
Hey, Mr. Pham, I must have messed up. How did you get the 1.6?
You take 15 volt times 1K. Divide 1K plus 8.2K. Voltage divider.
Yeah, that's what I thought, but maybe,
That's 1.6.
yeah, maybe I just messed up on my thing because
Okay.
I thought it was a voltage divider. Okay, thank you. I'll just have to
Yeah.
do it.
That's just a voltage divider. And the saturation voltage they give normally they give it to you. No matter whatever they give. And this is the key, the solution for that. Okay. And that will be you can go into more detail here. Okay. They're telling you this right here, 0 to the 1.63 volt. That means they less than the reference 1.63. So output will be negative. Saturation from this point to this point, they higher than the reference 1.63. So output go into positive saturation. Okay, from this point to this point, sideways less than the reference. So that's why output go to the negative saturation. And now they go back higher than reference. So that's why they go to positive saturation. Basically, that's a very, very simple, okay? Make sure you're looking into the circuitry, you know that comparator. And next thing is what they try to compare. Okay. And now, effect of input noise on comparator operation. Okay. Basically, you get compared to the route. And this is a V in. Okay. Compared to the 0. However, your input right here, you can see your input get too much noise. Okay. So that's why, they can see, you can see they try to get away from the noise. That's what they show up to you here. Okay. So this is your V in, and this is your output, V out max, positive saturation, negative saturation. I believe they can get some more explanation. Let's see here. Reduce the noise effect, okay, with the heterogeneity. Comparator with the positive feedback for heterogeneity, assume that output voltage is at its positive maximum plus V saturation. The voltage fed back to the non-inverting input is V upper that point and is expressed at V UTP equal R2 divide R1 plus R2 times V out max. Now see, when the output is at the maximum positive voltage and the input exceeds the upper trigger, the output switch to the maximum negative voltage. Okay, now you see what they're telling you here. Now they get you can see they get the feedback. R1 is the feedback, and also you get a R2. Okay. Normally, you looking into this circuitry, and sometimes you will be get confusion. Look like they can be what amplifier? Can you tell me? If you just look into the circuitry, can you tell me this? You think that's what the amplifier? The thing is they get R1 and R2.
It's an inverter.
I said, when you just look into that and maybe you recognize that can be what type of amplifier.
Is it inverting?
Cannot be inverting. How do we know? The thing is feedback inverting have to go to the negative, right? It's not a positive. If you're looking into that, you know the inverting amplified, then the resistor must be connected back to the negative, not positive. So cannot be inverting. So what else you can see? Can think they can be amplifier. What amplifier? The first thing you can see, I can tell you. You think that look like non-inverting. Is that right? The thing is we already get through the non-inverting.
Yeah, non-inverting.
However, how come this cannot be non-inverting?
Because the input's got to be applied to the positive.
Exactly. Input have to be applied to the positive, not the negative. So in this case, there will be a comparator. The reason is they adding the R1 and R2. Okay, they try to make less noise. Okay, using the what they call a hysteresis. So the first thing they need to calculate the upper trigger. That means upper trigger, what the voltage supposed to be. You take the V out plus time R2 divide R1, R2. That means you want the voltage here. Voltage at this point. Okay? That's what they call upper trigger. So when that's why they show you right here. Input when they go to the upper trigger here. Okay? Then what happened? When the output is at maximum positive voltage and the input exit gets higher than the V upper trigger. Okay? The output will be switched to the maximum negative voltage. Automatically, they go to the negative saturation. Okay? Let's see, we can get any picture here. Okay, they still. Now, they calculate that when they go into negative saturation, they calculate the lower trigger. Same thing, equal minus V out saturation divide R1 plus R2. So the first thing what you need to know, you need to calculate the V upper trigger. Okay, then you have to calculate the lower trigger. And the formula we already telling you. Okay? They say when the output is at the maximum negative voltage and the input goes below lower trigger, that means less than lower trigger, the output switch back to the maximum positive voltage. Okay, that will be telling you, you get the upper trigger. So when your input higher than upper trigger, then the output they change from positive saturate to the negative saturate. And when the negative saturation here, okay, lower trigger, okay, so they will be higher than lower trigger, they up trigger again, going back, that using for lower trigger point.
Mr. Pham, hold on before you go forward.
Yeah.
Go back to the first trigger. Okay, now, first of all, two things I need you to do for me. Number one, can you give a better definition of what hysteresis is? And then number two, can you put some numbers with the upper and lower trigger so we can get a clearer understanding?
Yeah, that's what I go here.
Okay, but okay, what's a more clearer definition of hysteresis?
Okay, they try to avoid the noise as much. I can show you your input here. You see that?
Right.
And basically in the input, you get a noise. Okay? So basically, the noise can make a messing up for the output trigger. So now they need to calculate the upper trigger first, that it did lie here. And they calculate the lower trigger here. Okay, so see, divide trigger only once when upper trigger or lower trigger point is reached. Okay, so basically this is just sideways, too much noise. Okay, so the first trigger only higher than upper trigger. Okay, then they can change it. Okay, and now this sideways go into this point here. So you can see they get only 1 point lower trigger, and now they change it. Okay, you see they say divide trigger only once when upper trigger or lower trigger point is reached. Thus, there is immunity to noise that is riding on the input signal. Basically, when the signal gets too much noisy, so that's why they need to using what they call a heterogeneous. Okay, this is the example here. They're using the reducing noise. Now, we see. First thing you see the circuitry, they want you to calculate the upper and lower trigger point comparator. Assume plot V maximum saturation 5 volt and minus V saturation minus 5 volt. Okay, what you have to do? First thing, yeah.
So basically you put that information that you just gave us, you put it back into the formulas that you just gave us above?
Yeah, the thing is when they want to hit the region, then what the first thing you have to do? Calculate the V upper trigger and V lower trigger.
Right.
So now, if I'm doing a calculation and I get the upper trigger is plus 2.5 volt, you understand how do I get that voltage? Okay.
So you said the assume V max, so plus 5 volts times what is it, R2, and then add R2 and R1 up and divide them or something?
Exactly.
R1 plus R2, yeah, voltage divide.
So that's how come you get plus 2.5 volt.
Right.
And if you calculate the lower trigger point, same thing, only thing they say have to be minus 5 volt time R2.
Okay, there we go.
That's the first step you have to do. Okay, let's see what's going on here. No more. See, and you, depending on the signal they given to you, okay, and you're able to get the output. How do we get? First thing, you need to draw the upper trigger. Like if you calculate here, is 2.5. So you get 2.5 volt here. And this is a negative 2.5. Okay, so when your sideway hit the first point here, okay, then you can get upper trigger, V in less than upper trigger, you get negative or positive, depending on the connection. Okay, input connect to the negative, output go for the upper trigger or lower trigger.
Mr. Pham, you was looking at the lower trigger on that one you just did.
Yeah, right now at this point right now here, right?
Right, but I'm saying when you was,
input less than upper trigger, right? This is the upper trigger at this point right here.
right,
So input less than upper trigger, telling you input less than upper trigger, okay? Then the output will be positive saturation. That means input positive higher than input negative. Okay, that's only the first point. Okay, then you have when they go into negative saturation. Okay, and this is a very lower trigger point. Only one point here. They intersect here. Okay, so when the input higher than upper trigger, output go to the negative. Okay, on this point, they will be less than, okay, the trigger point. So they get positive saturation. That's just for your understanding. You see, but you don't have to do anything. Okay. Only thing is when you keep going up to university, that will be really you have to understand. Okay. So basically for the comparator, that's a very simple thing. Okay. So do you get any question on the comparator? Basically not important to your guys. Okay. Not much application using the comparator. Basically for the whole course, very important will be what amplifier for bipolar transistor. Okay, for the operational amplifier, for the filter, and for the JFET. That's a very important thing, and we're using all the time. Okay, you get any question? If it's not, okay, make sure you go into website, download the handout for the JFET. I will be start the JFET now, okay? To be in electronics, you must understand the JFET, okay? That's very important to your guy. Let's see what I need to do.
Teacher,
Yeah,
a question. The op-amp used for amplifier is the same thing, is the same that used for comparison?
You mean using the same for comparator?
The op-amp that you use to make a circuit of comparator is the same that using for op-amp, right?
Right, they're using the op-amp. However, they build a comparator circuitry.
Yeah.
And you have to understand the detail comparator, how they work it.
Okay.
Okay?
Right.
Just wait for me. I need to download the new handout JFET. Okay, make sure you download for this handout. I said that are very, very important to you to understand. Let's see. Okay. The JFET, that's a Johnson field effect transistor. Here, a type of FET that operate with a reverse bias PN junction to control the current in a channel. Depending on their structure, JFET fall into either of two categories, N channel or P channel. Okay, so basically, JFET they can get the N channel JFET or P channel JFET. In the bipolar transistor, what you get a NPN transistor and a PNP transistor. JFET the same thing. Only thing is they can say either N channel JFET or the P channel. Okay, how do we recognize? This is a symbol for N channel. Okay, the first thing you can get this what they call a drain D, and this will be the gate, and this will be the source. In the bipolar, you can get the base, the collector, and the emitter. In the JFET, they can say this is the gate and the drain, and this is the source. And this is the P channel. What you see the difference between N channel and P channel? When you're looking into the symbol, you're able to tell me, is it an N channel or P channel? What's the difference? How do we know?
The direction of the arrow.
Exactly. Look into the arrow. Arrow right here. This arrow coming in. And this arrow coming out. Very simple thing, but you must know, like the bipolar transistor, how do you recognize NPN transistor or PNP? That means the same, the arrow go into the admitter or leaving the admitter. In the JFET also, you get an arrow. Go into the base, go into the gate, or leaving the gate. Okay, that will be defined N channel or P channel. Okay, and this is a little more physical show you on the N channel. So at the gate and the drain in here, they get the positive P side, and that will be N channel. Okay, N side. Contain the electrode. Same thing on the source on P channel, then this will be N side, okay, and this will be P channel. So that's just a very basic definition. Now, DC bias, N channel, and channel JFET. Okay, if you're looking into that, it will be N channel. The gate connect to the negative voltage VGG, and the drain connect to the positive voltage VDD, and the source will be routed. Okay, this is the explanation. VDD provide a drain to the source voltage. Okay, that means from a drain to the source voltage, and supply the current from the drain to the source. Okay, VGG set the reverse bias voltage between the gate and the source. Okay, so basically VGG negative connect to the gate and positive connect to the source and connect to the route. The JFET always operate with the gate, source, PN junction reverse bias. Okay, they're not working like bipolar, forward bias. They will be reverse bias. Okay, that's what you need to read over. Now, try to see what's going on. When you're looking into this circuit here, okay, they connect the meter to the gate, measure the voltage, and they connect the meter to the drain and connect the current. Okay, see what happened on this circuit here. That they telling you this is a negative voltage. Okay, more negative voltage. Then you're looking on the current ID will be lead current ID. And now you understand this is a channel right here. Okay, from the drain to the source. Okay, if the drain narrow, okay, then lead electron moving, so you get a lead current. Okay, so more negative voltage at the gate, they're telling you you get a lead current going from the drain to the source. Okay, and now in here, this is here. They change the voltage at the VGG. You can see VGG now will be lead negative. Then this one, they're telling you the channel wider, so more current will be flowing from the drain to the source. So now you see more current. Okay, that basically telling you current flowing in NPN, in N channel JFET controlled by the channel. If wider channel, more current flow. Okay, if the narrow channel, less current. Okay, and this is a symbol for the JFET. Okay, the thing is you have to working on that on the lab also. So they said right here, greater than VGG narrow the channel between the Y area, which increase the resistance of the channel and decrease the current ID. ID means drain current. IG means gate current. IS means source current. Okay? So when you see the symbol, you have to recognize right away. It is an N-channel JFET or P-channel JFET. And they get the three terminals. One will be the gate, and next one will be the drain, and the source. And basically, current will be flowing from the drain to the source. And that will be controlled by the gate voltage. Okay? Get any question? The thing is you have to read it, okay? You have to read the handout, okay? Reverse bias of the gate source junction with a negative gate voltage produce a depletion region along the PN junction, which extend into the N channel and thus increase its resistance of restricting the channel width. That means more resistance. That means the channel will be narrow. Okay. Now, looking into this picture here, you can say VGG, you can change it, change the value. So when you change the value, it is less negative voltage to the gate. And they also show you can get more current. The thing is the channel wider, okay? More current from the drain go into the source. That's a very simple thing. Let VGG widen the channel between the Y area, which decrease the resistance of the channel, and that will be giving you more current, okay, in the ID. Okay, up to this point, you get any question?
Yeah.
Yeah, go ahead.
So this device is control the main current using voltage, and
On the gate.
bipolar transistor use control the main current using current, right?
Okay, in the bipolar transistor, okay, basically you get a voltage at the base that will be turned on the diode from the base to the ammeter, okay, and basically that will be controlled. That you can see that will be given to you the current IB, and more or less voltage to get a more or less current, and that current also control the bipolar transistor. Okay, and bipolar transistor can get amplified. That means they amplify the current IC equal beta times IB. On the JFET, they just telling you, basically, you apply the voltage into the gate, and that negative voltage, they will be changing the channel from the drain to the source. Wider channel, you get more ID current. Okay? If the narrow, you can get less current. And they showing you right here. Okay? If you get a more negative, this channel will be narrow, so less current. Okay? If this in this, so here, you can get a less negative voltage. That telling you you can get more current ID.
Okay, thank you.
Now,
The JFET is a voltage control device and the bipolar transistor is a current control device.
Yeah,
now you're looking into this circuitry. You can get the JFET with the gate connect to the route. And now you're changing the VDD. Okay? Try to see what happened. On the graph in here, this is what telling me. What is it here? What stand for?
Oh, you mean the drain the source voltage or what?
VDS.
VDS, that's drain the source.
Exactly. You can see. They say VDS. That means the drain to the source voltage. Okay? That means from the drain here to the source, that's the VDS. And this stands for
Drain current.
drain current. Okay? And you can see, let's see, with JFET with VGS equals 0 and a variable VDS. That means you can change VDD. That makes the VDS changing. Okay? So there to the VDS, they can be changing. And if you're looking into here, that's the maximum current JFET can get. That's what they call IDSS. Okay? So this is the ID, the VDS changing up to this point. Okay? Then the area here, JFET will be using that as the resistance ohmic area. Same thing on the bipolar. You get this area will be a saturation. On the JFET, they will be working at the resistance. That's what they call ohmic area. And then from B to C here, VGS equals 0. You understand me? When you changing the VGS, okay, you get the current increase. More VGS, then you get a less current ID. However, at the beginning, VGS equals 0. That's what you get the maximum current ID. Okay, so now you can see if VGS equals 0, then you get a maximum current. That's what they call a IDSS. Okay? IDSS means the maximum current when the VGS equals 0. So from B to the C, this area they call a constant current area. Okay? That means the current in this area all the time will be equal IDSS. Then now you try to increase more VDF, you get into a breakdown area. You can see exactly the same bipolar transistor. Okay?
Hey, Mr. Pham, what does that mean, IDSS? Current drain the source with the source shorted?
Right, with the VGS shorted. Remember, VGS equals 0. Then you get the maximum current, that's what IDSS. And later on, you can see IDSS that the bill with the JFET, they gave it to you. That means whenever VGS equals 0, then the current must be equal IDSS.
And when you're using the JFET, basically we want to be operating in the constant current area, correct?
Yeah, that's
Okay,
a constant current. And you
thank you.
understand, at this point, what they call a VP. VP stands for pin off voltage. That means if the VDS higher than VP, then JFET now will be in constant current. You can see this is a constant current saturation. And whenever VDS higher than VP, if they less than VP, JFET now will be in the ohmic region. That means they can working like resistance. And I want to make sure I emphasize for you, what is that IDSS? What is it? Who can answer to me? What is the IDSS?
I thought we said that's the current from drain to source with the source shorted.
That is the maximum current
Oh, okay.
with the VGS equals 0. So whenever VGS equals 0, and you get a current maximum, that's what I call IDSS. However, IDSS, you cannot calculate it. That bill in the JFET in the manufacturer, they give it to you. The thing I try to help you understand, okay? The thing is that very important at this time. Most the device they build now, they're using JFET instead they using bipolar transistor. The thing is when I work at the university, I can do homework or the test, but I not quite understand. So that's why I really want you to understand. In order to do it, you must reading and now keep over and over. Okay. Now, see what's going on here. The maximum drain current of JFET occur when the gate source VGS equal 0. That's very good explanation. That means when VGS equals 0 and the drain to the source current ID go to the maximum and they call V ID at F. The drain current is almost constant in the region between VP and VDS maximum. VP means ping off voltage. That's what you have to get along with that. Otherwise, they're talking about VP. You don't know what that stands for VP. That's a ping off voltage. Okay. The drain current, okay, constant in the region between VP and VDS. Okay, that means between VP and VDS, the current will be constant and they equal ID at F. If the drain voltage is too large, the JFET will be breakdown. That means right here. Okay, you keep changing that voltage and that will be a breakdown. We don't want that. Okay, see next. JFET acts like current source when it is operating along the almost horizontal path of the drain current. That means between minimum of VP and the maximum of VDS. The minimum voltage of VP equals a ping off voltage. The maximum voltage VDS max equal a breakdown voltage. Between the ping off and the breakdown, JFET act like current source with the value of ID at S. ID at S stands for the current from the drain to the source with shorted gate. That means with the VGS equal 0.
I was short of gate.
Ohmic region. The almost vertical part of the drain current equal ohmic region. That's equivalent to the saturation region of bipolar transistor. So basically, bipolar transistor, they call saturation region. In the JFET, called ohmic. The thing I did, I tried to combine, after I understand, I try to combine whatever you need in order to understand the JFET. In order to do it, I also recommend read it over. So you can see some students, they've been in this program maybe too many years. 2 years, 3 years, 4 years, 5 years, 6 years, 7 years. And now they can get a much better understanding. Okay? The first time you get through it, I don't believe, I don't see you can really understand that. Now, next, the JFET got cut off voltage. The value of VGS that make ID approximate 0 is the cutoff voltage VGS off. So They can ask you what is the VGS of. That is the value of VGS. That make ID approximately 0. Then you get the voltage VGS, they call VGS off. The JFET must be operate between VGS equal 0 and the VGS off. So, in order to get a VGS off, you understand the ID is supposed to be 0. Okay? The JFET must be operate between VGS equal 0 and VGS off. Now, comparison of the ping off and the cut off. VP is the value of VDS at which the drain current become constant and is always measured at VGS equal 0. VGS off and VP means ping off voltage, are always equal in magnitude, but they will be opposite in the side. That means VGS off and the VP, they will be on the time. Okay, will be the same but different polarity. VGS off equal negative, then VP equal positive, and reverted. This VGS off and VP you can not calculate it, they given to you with the JFET manufacturer. Data sheet usually will given either VGS off or VP, but not both. Okay, so if they given you VGS off equal -5 volts, and you understand right away, VP will be positive 5 volts. On the time, they be the same value, but they opposite. So that's why in the manufacturer, they just given you only one, not both. Either they given you VGS off, or they given you VP. If they given you VP, then you know VGS off. Okay, up to this point, any question? The thing I want, what I want, next week we will keep going on the JFET, and after holiday, I want the first week of the January, I want to complete for the JFET. They will be the same bipolar transistor. First thing we'll be learning how to do calculation for DC bias. That means JFET the same bipolar. They need the DC power supply to make it work. Then the next part will be JFET for amplifier. And they can get the source, common source amplifier, common drain amplifier, common gate amplifier. You can see they compare to the bipolar. You get common base amplifier, common emitter amplifier, common collector amplifier. Okay, that is almost the same thing. Okay, so you get the time, try to reading more. Okay, next week we get only one day lecture on a Monday. Then I try to go at maximum we can get. whenever you're looking into the JFET circuitry, you know what to do, how to do it. That's perfect. Okay, any more questions? If it's not, so Mr. Sam, are you ready for the quiz?
Yes, sir.
Okay, let me stop on that guy.
Okay, so we're going to do eQuiz number 8. So make sure you download it from the website. Okay, let me go ahead and get started. Share screen. Okay, so here we go. Okay, so that's pretty much it. Let me see chat. Enroll to spring 2022. So can you please show us 3? Okay, so number 3, let me see, and slideshow. Let me see number 3. So number 3 is right there. Yeah, we'll let you know about the spring registration as soon as we get the code from the office manager. So we'll let you know in January. Right now, we do not know yet. Okay, let me see number 2. Okay, number 5. All right, so number 5 is next. So that's number 5. See chat. Okay, look like everything's good. Okay, like I said, that's good. So make sure you upload it to the website by 12 noon tomorrow. And we'll see the rest of you in the lab. Okay, look like question number 9. Okay. So that's question 9.
Sam, can you show me question 18 again, please?
Okay.
Thanks.
Let me see, stop this one here. Let me see, we're gonna be stopping this one here, share, stop, let me see, stop sharing. Okay, we're gonna stop share first. Okay. Oops. Okay, number 18.
Thank you.
Welcome. Okay. So you missed it. If you're missing all this, make sure you just go watch the video. I'm not running anymore. Once Mr. Pham uploaded onto the website, so you can go back and watch that. Okay. Thank you. Make sure everybody upload it, and we'll see the rest of you in the lab tomorrow.
Okay, thank you, Sam.
Thank you.
teacher.
Bye-bye.
Okay, so any question to me? You understand the quiz? That will be related into the lab 4. When you do the lab 4, you have to take unit test, okay? So if you can get the quiz done easy, that will be helping you to get the test in the lab 4 done, okay? So if you don't have any more questions to me, so good night, everyone.
Thank you. Good night.
Thank you.
Good night.
Bye.
I noticed.